The Foundations of Geometry by David Hilbert.
Chapter 5, Desargues' Theorem. Section 22, Desargues' Theorem and its demonstration for plane geometry by aid of the axioms of congruence. Of the axioms given in sections 1 through 8, pages 1 through 14, those of group 2 through 5 are in part linear and in part plane axioms. Axioms 3 through 7 of group 1 are the only space axioms. In order to show clearly the significance of these axioms of space, let us assume a plane geometry and investigate in general the conditions for which this plane geometry may be regarded as a part of a geometry of space in which at least the axioms of groups 1 through 3 are all fulfilled. Upon the basis of the axioms of groups 1 through 3, it is well known that the so-called Theorem of Desargues may be easily demonstrated. This theorem relates to points of intersection in a plane. Let us assume in particular that the straight line upon which are situated the points of intersection of the homologous sides of the two triangles is the straight line which we call the straight line at infinity. We will designate the theorem which arises in this case, together with its converse, as the Theorem of Desargues. This theorem is as follows. Theorem 32, Desargues' Theorem. When two triangles are so situated in a plane that their homologous sides are respectively parallel, then the lines joining the homologous vertices pass through one and the same point or are parallel to one another. Conversely, if two triangles are so situated in a plane that the straight lines joining the homologous vertices intersect in a common point or are parallel to one another, and furthermore, if two points of homologous sides are parallel to each other, then the third side of the two triangles are also parallel to each other. As we have already mentioned, Theorem 32 is a consequence of the axioms groups 1 through 3. Because of this fact, the validity of Desargues' theorem in the plane is, in any case, a necessary condition that the geometry of this plane may be regarded as a part of a geometry of space in which the axioms of groups 1 through 3 are all fulfilled. Let us assume, as in sections 13 through 21, pages 23 through 45, that we have a plane geometry in which the axioms of group 1, 1 and 2, and groups 2 through 4 all hold. And also, we have introduced in this geometry an algebra of segments conforming to section 15. Now, as has already been established in section 17, there may be made to correspond to each point in the plane a pair of segments, x and y, and to each straight line a ratio of 3 segments, u, v, w, so that the linear equation ux plus vy plus w equals 0 expresses the condition that the point is situated upon the straight line. The system composed of all the segments in our geometry forms, according to section 17, a domain of numbers for which the properties 1 through 16 enumerated in section 13 are valid. We can therefore, by means of this domain of numbers, construct a geometry of space in a manner similar to that already employed in sections 9 or in section 12, where we made use of the systems of numbers omega and omega t, respectively. For this purpose, we assume that a system of 3 segments, x, y, and z, shall represent a point, and that the ratio of 4 segments, u, v, w, and r, shall represent a plane, while a straight line is defined as the intersection of 2 planes. Hence, the linear equation ux plus vy plus wz plus r equals 0 expresses the fact that the point xyz lies in the plane uvwr. Finally, we determine the arrangement of the points upon a straight line, or the points of a plane with respect to a straight line situated in this plane, or the arrangement of the points in space with respect to a plane by means of inequalities in a manner similar to the method employed in the plane in section 9. Since we obtain again the original plane geometry by putting z equal to 0, we know that our plane geometry can be regarded as a part of geometry of space. Now the validity of Desargues' theorem is, according to the above considerations, a necessary condition for this result. Hence, in the assumed plane geometry, it follows that Desargues' theorem must also hold. It will be seen that the result just stated may also be deduced without difficulty from Theorem 23 in the theory of proportion.
The Foundations of Geometry by David Hilbert. The material contained in the following translation was given in substance by Professor Hilbert as a course of lectures on Euclidean geometry at the University of Göttingen during the winter semester of 1898 and 1899. It was translated by E. J. Townsend, Ph.D., University of Illinois. The text was downloaded from Project Gutenberg with the following notice. This ebook is for the use of anyone, anywhere in the United States and most other parts of the world at no cost and with almost no restrictions whatsoever. Read by Jim Renholt. Programming and illustrations by Jim Renholt. 2019. Portrait of David Hilbert by Rita Ray Renholt. Thank you for listening.